Hello everyone and welcome to this lecture on ensemble methods in deep learning. So what are ensemble methods? Ensemble methods in deep learning combine the predictions from multiple deep neural networks to improve performance, right? That is we will reduce either overfitting or underfitting and increase the robustness in that the process. Okay, so why do we use ensemble methods? Basically, this combination of multiple neural networks, why do we use is deep learning models are highly flexible but prone to overfitting or underfitting. Okay, so that is the case, and to ensure that ensembles, what they do is they smooth out the predictions by leveraging multiple models that are trained differently. All right, there are basically three uh, they help overcome challenges like unstable training or local minima. Local minima is where we uh, I guess I have explained it earlier, where we think that we have reached the minimum uh, error condition, but it is not the minimal error condition. It's just a local one, and what we our goal is to reach a global minima of the errors. Okay, so it will be like the error is decreasing at a certain point. After a certain point it will increase, but then it will again start decreasing. Okay, and it will finally reach the lowest point, and that is the global minima for errors, and uh, which is what we intend to uh, get to. All right, so the types of ensemble learning, there are three: bagging, boosting, and stacking. We'll see them one by one. Bagging, basically, it reduces the variance. Variance is associated with overfitting. All right. When we say variance, it basically means overfitting. So the overfitting, as we have seen, is the case where the uh, trainings of multiple DNNs on different subsets of data. Predictions are averaged, that is for regression, or for majority voting, uh, combined using majority voting for classification. Okay, so in variance, what happens is the data, when we trained our model, it learns that particular data in such a way that it also uh, takes into consideration the noises. Okay, so what are noises? The data which occurs once in a while and it is not very important. All right, and we don't want to include noise in our training process. But when we have variance or overfitting, we have considered noise. All right, so to avoid this situation of higher variance or overfitting, what we do is called as bagging. Okay, so bagging can be used to avoid the uh, s- overfitting, or it can help in reducing the variance. All right, the steps is, we divide the data set. This is the entire data set. What we do is we divide it into different samples. Okay, samples by replacement. What it means is, sampling by replacement means that data that has occurred over here, it's not can also occur over here and can also occur over in dataset 3. Okay, so there is a different combination. There is a different combination of dataset, but it is not unique. Okay, it is not that dataset 1 is unique, dataset 2 is unique, and dataset 3 is unique. Okay, it is a case where all the three can have some or the other data points which are common to each other. Okay, so this is something called as random sampling with replacement. All right, and what we do is, this step of creating the data sets is something called as bootstrapping. Okay, so bootstrapping is this process, and then we pass it to the models. All right, and those models are separate. that is model data, you will see over here. It's deep learning neural network 1, model 2, and model 3, and we take the predictions of those models. All right, and depending on what problem we are solving, if the problem is a classification problem, then we take a simple majority of votes. Okay, a simple majority of the votes. So that will be, if say class 1 has the higher number of votes, then our prediction will be class 1. All right, and if it's a regression technique, if the values of y are all continuous values, not discrete values, as we have in classification, if we have continuous values, then it's a regression problem, and in that case, what we do is we take the average of all the predictions. All right, and that is our final answer. Okay, so this is the process of bagging, uh, in how it works. And practical implementations is done in CNN, where you can have multiple times of processing with different initialization of data samples, and aggregate predictions from all the networks are used during inference. Advantages is it reduces overfitting, as we already discussed. It is used to reduce variance, right? And variance is nothing but the case of overfitting. By averaging out the random noise, it increases the model robustness against noisy and imbalanced data. All right. Limitations is it's computationally expensive. It requires multiple deep neural networks. Since it requires multiple deep neural networks, it is computationally expensive. All right. Examples of example use cases are image classification. Okay, so we use it in image classification or in convolutional neural networks. We are not there yet. We have not yet discussed convolutional neural networks, but in a gist, if I have to tell you in short, it would be that convolutional neural networks are used for image processing. Okay, so we'll see that when we come to that. uh, Boosting. Boosting is where so we saw one type, that is bagging. Now we are to the other type, which is called boosting. The concept, it is reduces bias, and bias is underfitting, associated with underfitting. Okay, so bias is a preconceived notion of the data. All right, I say this repetitively. Bias is basically, you can have either bias in favor of something or in opposite of something, and basically that is, we have some preconceived notion, some assumptions made. Okay, but those might not be true. Those assumptions might not be true. So uh, it reduces bias by sequentially training the deep neural network. Each model learns from the mistakes of the previous model, and it basically improves. Okay, so something like this, we'll have a we'll train a deep learning neural network, which is a weak learner. Okay, and then what we do is, which is deep learner, which is trained on the training data, and then we evaluate the errors of the misclassified samples. Okay, after evaluation, we assign higher weights to the misclassified samples. Okay, and after assigning higher weights, what we do is basically we retrain that on the same data. um, we retrain the model on the same data, and if this time the predictions, there's an if involved over here. All right, so based on which one is the better one. Okay, it might so happen that after assigning higher weights or lower weights, or doing some fluctuation with the weight, we do not actually improve the accuracy of the deep learning neural network, but we end up hampering the accuracy of the deep learning neural network. So in that case, what we'll do is we'll use select the stronger uh, of the uh, stronger deep learning neural network. Okay, so whichever one is the strongest, we'll select that. So basic idea is we move from the weaker learner to the stronger learner. All right. So the stronger model is what we intend to achieve, and this is an iterative process. Okay, it is not a one-step process. It is an iterative process. So continually, for the number of times that the user specifies, continuously this process happens of replacing the weaker learner with the stronger learner, and eventually, what we wish to arrive at is the stronger learner at the end. Okay, so this is something called as boosting method. The practical implementation is when we have sequential training of deep neural networks, where each model is trained on a weighted loss function emphasizing misclassification. Now, sequential training is done in recurrent neural networks. Okay, so that is where you could have your implementation of boosting algorithms. Okay, it reduces the bias. As I said, bias is associated with underfitting, so it makes it effective and for underfitting problems. Okay, it improves the performance of imbalanced data sets. Limitations is it is prone to overfitting. Okay, since uh, we have trained our model multiple number of times, it could happen that our model actually ends up being overfitted. Okay, especially when weak learners are highly flexible. All right. Computationally, it is expensive. Again, this is also computationally expensive because you are sequentially training the model on the entire data set again and again. All right, so that's a very high cost to bear. Use cases is test classification, boosting uh, to improve performance on dataset with minority classes, such as detecting rare keywords in documents. Okay, so this is an application of natural language processing, detecting the rare keywords in document. Then we come to stacking, the final concept, which is stacking. The concept of stacking is it's similar to, if I have to say in few words, it would be similar to bagging, but instead of averaging or this voting, we use a meta learner, a different meta learner. All right. So stacking improves generalization by combining diverse models through a meta learner. All right. Instead of learning the errors sequentially like boosting or stacking, uh, stacking learns how they to best combine the predictions from multiple base models. All right. So train multiple models, uh, the training different deep neural networks uh, independently on the same training data, then generate the base predictions. Each of the deep neural networks produces predictions on the validation data. We create meta features. Okay, so prediction from the base models are used as inputs for the meta model. Okay, so over here, if we see, uh, this part is the same, but after this, instead of using it either using a majority vote or average, we actually introduce a new model over here. Okay, DNN model, which actually takes these as inputs, the outputs as inputs, and then gives a output by itself. Okay, so that is stacking. Okay, so the level 1 of model is a new model, often a shallow neural network or a logistic regression, which is trained to learn the optimal combination of the base mod or output. And the final prediction is, of course, the one given by the meta learner. So during inference, the base model generate the predictions, and the meta model combines them to produce the final output. Okay. Uh, Practical implementation is to train deep neural networks in parallel, use cross validation to avoid leakage when generating meta features. Meta learners is trained to on base model predictions, not raw input features. The common meta learners is logistic regression, shallow neural network, and linear regression. So if you have a background in machine learning, you already know what a logistic regression is, a shallow neural network is, not shallow neural network, sorry, what a linear regression is. Okay, but shallow neural networks we have seen. Okay, shallow neural networks is the basically opposite of deep neural networks. Okay, so in meta models we use shallow neural networks. Basically, the ones which do not have too many hidden layers are the shallow neural networks. Okay, so that is the case. If we have to see the differences between bagging and boosting, that would be these are the differences in training. The models are independently trained in bagging and sequential for boosting. Focuses on reducing the variance. Bagging does focus on reducing variance, and boosting reduces the bias. Data handling is done that in a way of randomly sampled subspaces, subsampled spaces for bagging, and all the data is used for boosting. Aggregation is simple average or voting, and a weighted combination of the model, it says over here, but basically it's the final model, okay, which wins the race. Real world application. Wait, am I going? Oh, I'm so sorry. I guess this is a repeated slide. Okay, sorry. It gives a real world application in deep neural networks, sorry, uh, for bagging and boosting. So we already saw that bagging is a good idea for convolutional neural networks or CNNs, and boosting is a good idea for, say, uh, the textual or fraud detection or such use cases. Okay, so with that we come to the conclusion of this lecture, which was on ensemble methods in deep learning. See you in the next lecture. Thank you.